Okay, so we have already seen the concept of active and reactive power flows and how sign is assigned to a reactive power flow with respect to source and load. Now we'll see an example with multiple loads. Loads in the sense multiple active and reactive power loads. So let me draw the circuit. We have a reactance of 5 kVAR, 5 kVAR connected like this to a load which is B and 2 kilowatts. Now from here I have a capacitor like this. This is connected to a source. This source is 380 volts. Now from here another capacitor, then another load here which is E 8 kilowatts, and I have a motor. So the motor is of 14 kilowatts and 8 kVAR. The current here is I. Then this is 2 kilowatts. This is 9 kVAR. This is 16 kVAR. This is A. So A, B, C, D, E, and okay, one reactor is missing. Here I'll include that, which is of 7 kVAR, which is F. Okay, so these are the components in the circuit. So let's represent it in another form. I'm representing the source like this, which is 380 volt. Now say I have an electrical point like this, which is represented by this line. This is the same electrical point. Okay, some electrical terminal. Now I'm drawing different components. My A is connected like this, then my D is connected like this, then my E is connected like this. This is B, this is C, then F and M. Now, so this is a circuit with active and reactive power loads connected to a 380 volt source. Now all the loads are assumed to be directly connected to the 380 volt supply. So our aim is to find different the total reactive power, real power and apparent power absorbed by the circuit using the power approach, which we have seen in the previous lectures. So we do not have to worry about the way the loads are interconnected. We simply draw the block diagram like this with respect to active and reactive power. We are going to represent active and reactive power by indicating individual loads and their direction of active and reactive power flow. Now load A. Where is load A? This is load A. Load A is inductive, right? Load A is inductive. So it absorbs reactive power. It absorbs reactive power. So I'm drawing arrow like this, and that is 5 kVAR. 5 kVAR. Right. Now, what about load B? I have load B, which absorbs active power, which is 2 kilowatts. 2 kilowatts. This one. Then I have load C, which is capacitor, so it generates or delivers reactive power. So this is 16 kVAR. Now my motor is receiving an active power of 14 kilowatts, and it is receiving a reactive power of 8 kVAR. Now my load F, where is load F? That's a reactor, right? So 7 kVAR is absorbed. Then E is absorbing active power 8 kilowatts. Then what about D? D is delivering 9 kVAR. So from this we can this power flow diagram. This is a power flow representation of the circuit. From here we can directly find the total reactive and active power, reactive, active, and apparent power, even the current and power factor also. So what is the total active power? 2 plus 8 plus 14 equals, I'm writing here, plus 24 kilowatts. Why is it so? These are active power received, right? So these are contributed by active power loads. Now, what is my Q1? 5 plus 7 plus, then 7 plus 8, which is equal to plus 20 kVAR, right? So these are reactive power consumptions. Now, reactive power consumptions, then reactive power supplied by the capacitors. If I want to find reactive power supplied by the capacitors, so this is consumption, this is also consumption, this is supplied, Q2, which is equal to minus 9 is there here, minus 9 is there, then minus 16 is there, which is equal to minus 25 kVAR. So you can see the sign here, which is negative. Now what about the net reactive power? Net reactive power I am representing by Q net, which is equal to minus 20, this is plus 20, right? Plus 20 minus 25, which is equal to minus 5 kVAR. Now I can find the apparent power. What is apparent power here? Apparent power is equal to root of P squared plus Q squared, which is equal to root of 24 squared plus minus 5 the whole squared, which is equal to 24.5 kVA. Okay, now because the 380 volt source supplies the apparent power, we can find the line current by taking current equals apparent power supplied by the source divided by the voltage of the source, which is equal to, how will you find it? How will you get it? What is S here? 24.5 kVA, which is 24,500 volt amps divided by 380, which is equal to 64.5 amps. 64.5 amps. Now what about the power factor? equals cos phi L, which is equal to active by apparent, which is equal to 24 divided by 24.5, which is equal to 0.979 leading. Why I am writing leading here? Because the sign is negative, which means net reactive power is generated reactive power, right? When net reactive, but how we defined net reactive power? This is net reactive power absorbed. So net reactive power is absorbed. As net reactive power absorbed is negative, that means reactive power is delivered. So that is what we are representing. So the 380 volt source delivers 24 kilowatts of active power, but the source receives 5 kVAr of reactive power. This reactive power flows into the local distribution system. We can consider the source as the distribution system itself. So if the source is considered as a distribution system, then the reactive power flows into the local distribution system of the utility company, where it becomes available to create magnetic fields. The magnetic fields may be associated with distribution transformers, transmission lines, or even the electromagnetic relays of customers connected to the same distribution system. So that is what we have seen here. Now, if I want to represent the same thing as power triangle, as we have seen in the last lecture, how will I do that? So I'm going to represent represent different vectors showing the active and reactive power flow to form the triangle. How will I do it? So I have 16 kVAr in one direction. Where is that? I'll show this first, then 16 kVAr. Okay, 16 kVAr in one direction. Then 9 kVAr in the same direction. 9 kVAr in the same direction. Then what else? 9 kVAr is there, 16 kVAr is there. That's all right. Others are consumption only. This is delivered. So I'm representing in the same direction. This is 16 kVAr. This is 9 kVAr. Okay. Now, like this, I am taking active power. This is 8 kilowatts. 8 kilowatts. E. Here it's 8 kilowatts. Then I'm going to take 7 kVAr. What's the direction here? 7 kVAr. 7 kVAr is consumed. This shows reactive power load. Okay. Similarly, I have 5 kVAr also. Right. 7 kVAr, 5 kVAr. Then what else is there? 7 kVAr, 5 kVAr, 14 kilowatts. 14 kilowatts is also supplied, right? So I'm taking here 7 kVAr, then 14 kilowatts. See, this 14 kilowatts is parallel to 8 kilowatts. Okay. Then I'm again taking 8 kVAr. 8 kVAr. What is this 8 kVAr? 8 kVAr. 8 kVAr. Okay. Now, so this is the endpoint. 7, 14, 8, 16, 9. Okay, 9 is already accounted here. 9. Okay, that's all. Now, so this is the endpoint. This is my endpoint. 16 is there. 9 is there. Then 8 is there. 7 is there. 14 is there. 8 kVAr is there. So this is my endpoint. Okay. Now, if I want to, one more thing, there is a 5 kVAR, right? There is a 5 kVAR which is also reactive load. So let me start from here. 5 kVAR, what is the direction? It should be parallel to this 7 kVAR, right? So this is my 5 kVAR. Then I have a 2 kW. I have a 2 kW. That is also active power load. So load I am representing like this. So this is parallel to 8 kilowatts. 8 kilowatts is also active power load. So this is my starting point now. This is my starting point. This is my end point. This is my end point. This is my starting point. So I can draw the resultant like this. Like this. I can draw the resultant like this. And my resultant is 24.5 kVA, the magnitude of resultant, which is the apparent power. Now, if I want to represent the corresponding active and reactive power, I should make this a triangle. For that, I am making like this. I'm drawing like this. Let this be a triangle. So this will be the base of the right triangle, which is 24 kW. What is active power? 24 kW. Then this is my altitude, which is, what's my altitude here? What's it? 24. Then this should be, again, this is perpendicular to this and this is perpendicular to here. So this is parallel to, basically this is parallel to 5 kVAR, right? 5 kVAR. So this is 5 kVAR. 5 kVAR. 24.5, this is 24 and this is 5 kVAR. So this is how we draw the reactive and active power flow vectors to study the total reactive power, active power and apparent power consumed or generated by the net reactive, active and apparent power of a circuit.